Okay, so this is the last few pages of the notes packet, and really we're just going to highlight a few key things here. I am going to go ahead and read through it, just so that the pace of the video doesn't go too fast. So properties of ionic compounds. Up until now, you should have been able to practice all of the formula writing for the various polyatomic ions and metal cations and forming and writing names. If you need any help with any of those worksheets, please let me know. So this should be like the last page and a half of your notes. Properties of ionic compounds. So everything we've been forming up to now, they're called ionic compounds because they're made of a cation and an anion, a positive and a negative. Now, as we have seen, so I'm reading here the first paragraph, ionic compounds are composed of positive ions and negative ions, such as NaCl, which have a positive sodium ion and a negative chloride ion. The formula, though, only represents the ratio of positive to negative ions, okay, that would result in a neutral unit. The arrangement of these ions is not that of individual units, but rather as repeating geometric patterns where each positive ion is completely surrounded on all sides by negative ions. So even though the formula for NaCl is 1:1, this structure here is more of what a salt structure looks like, where there's maybe thousands of ions, but they're in the ratio of one positive ion to one negative ion. They're a repeating pattern. Okay, so each negative ion is completely surrounded by on all sides with positive ions. Now, this arrangement is called a crystalline lattice. Because the ions are arranged in this pattern, it is impossible to ever obtain a single NaCl unit, meaning we can't just have one Na and one Cl ion, period. Okay, the crystalline lattice arrangement is responsible for the properties of ionic compounds, and so as the term indicates, they are crystalline solids. Think about table salt, right? You put some in your hand, it is a crystalline structure. It looks like a crystal. A lot of that has to do with the geometric arrangement of its ions. Okay, so to melt an ionic compound, enough heat energy must be applied to break the attraction between each and every ion in the crystalline lattice, allowing the ions to flow or move freely. Because each ion is surrounded by other ions, this requires a tremendous amount of energy, resulting in high melting points for these compounds. This is a property of ionic compounds because of the amount of energy it takes to break the attraction between a positive and a negative ion. Most crystalline lattices or most crystalline structures, most ionic compounds have high melting points. Now, in comparison to each other, one may have, higher within the ionic compounds than another, but when compared to covalent compounds, which is the next unit we're going to look at, they are considered to be really, really high melting points. Okay, so further, to force them into the gaseous state requires another huge quantity of heat, giving these compounds also very high boiling points as well. Okay, and so here's a table just for you to kind of compare a couple of things. I'm going to switch colors here. This right here, NaI, well, there's no other example in there. If you look at KBr, NABR, okay, and then if we look at NaCl, something's wrong with this one. That one shouldn't be NaCl as well. MgO, CaCl2. I'm not sure what that one is supposed to be, so kind of ignore that one. But basically, this is a summary of the notes, a summary of the melting points and the boiling points for various substances. Okay, back to our notes. We're almost done here. An electric current can be conducted by the movement of charged particles. So you're probably aware that electrons moving through a wire are conducting electricity, but any charged particle, if it's free to flow, can conduct electricity. This explains why, as solids, ionic compounds are not good conductors, meaning they don't conduct electricity. If you had a piece of salt and you were to have a conductivity tester up to the salt crystal, it would not conduct electricity. But when molten, okay, they do conduct electricity readily. Now, most ionic solids will dissolve in water. It's another trait. Okay, we will explore the reasons why in our next unit of study. But when they do dissolve, the ions break apart from one another in their crystalline, allowing the flow of charged ions. So if they conduct electricity when dissolved in water, they are called electrolytes. And even furthermore, you have a degree of electrolytes: strong electrolytes, weak electrolytes, non-electrolytes. Okay, another interesting fact is that most gemstones are ionic. They contain metal ions, which give them their color. Now, we did a unit, I think last unit, with electron configurations. Certain metals, okay, produce certain colors. Now, these gemstones, they can be cut or cleaved, which leaves them with a perfectly smooth surface by tapping them with a small hammer at just the proper spot on the crystalline lattice. This tap shifts the ions in the lattice, causing negative ions to lie next to negative ions, and positive ions to lie next to positive ions. Since the like charges are repulsed by one another, the crystal splits along the line in the lattice, resulting in the beautiful surface of what we typically have on stones. Okay. Now, lattice energy. Okay, this is the energy that's released when 1 mole of ionic compound is formed from its gaseous ions. Remember that the reason atoms form bonds is to have 8 electrons in their outer shell, which gives them greater stability and lower energy state. I'm going to highlight that in a different color because that's pretty important. Okay, most atoms want 8 in their valence shell. Okay. As an ionic compound is formed, energy is released, taking the ions to a lower energy state with greater stability. Examine the table of lattice energies below. So here we have a few ionic compounds. They're all made of positive and negative ions. This is how much energy would be released when 1 mole of the ionic compound is formed. Okay, and it's in units of kilojoules per mole. Okay, now, as you should recall, energy, we did last unit, okay, is measured in joules or kilojoules. Note the negative value. In chemistry, when energy is released, the value is negative. Since the ions are going to a more stable, lower energy state, they are releasing energy, and that's why the value is negative. Okay, a compound's lattice energy value is a measure of the strength of the bonds between the ions in the crystalline lattice. The more energy released, the more stable the compound and the stronger the bond. Okay, and so if we were to look at this table above, think about the ones that are higher in value, so meaning more negative, okay, more energy is released. That talks about the more stability of the compound and how strong that bond holding the energy is together. Okay, can you look at the compounds in the table above and determine what factors might make one compound more stable than another? Okay, well, a lot of this has to do with maybe the ratio, what the charge on the ion is. For example, let's see if we can find any that are the same or similar. Okay, we can think of NAF and NAI, NABA, BR, and NaCl. Okay, so think about where these exist on the periodic table, and let me see if I can pull my periodic table up. May not have all. There it is. Okay, so here's my periodic table. Ignore what's on there. We have fluorine, chlorine, bromine, and iodine, and we have sodium. So we know that sodium forms an Na+, right? And we know that each of these forms a negative ion, -1. But look at their locations. Think about other things that we've previously talked about in this unit. For example, size, whether or not they are a big atom or a small atom. Some of those will contribute to why, and I gotta find my notes back again, why they might have a larger value, okay? And so we had F, Cl, Br, and I. Na was way over here. Let's see if we can find any patterns or anything. Think about F. Okay, this is a really, really small atom. Look how much energy it would take to form NaF compared to NaCl, where Cl is right underneath fluorine. It's a little bit bigger. Okay, maybe the attraction there is not as strong. Think about electronegativity. We just got done using that in this unit as well. Fluorine is super electronegative. It really, 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 really wants to get 8. And so fluorine is going to be holding on to sodium's one electron that it's wanting to give. And it releases a lot of energy whenever it forms. Okay, so just a few more sentences. We can also think of lattice energy as the energy required to break apart 1 mole of an ionic compound to form gaseous ions. But then we would have to change the sign to reflect a positive number, since energy must be added instead of being released. So watch the wording here, okay? If it's asking how much energy it would take to form, okay, that should be a negative number. If I want to break apart an ionic compound, then I have to put energy into the compound, and so that would be a positive number. And last but not least, it also makes sense that higher the lattice energy, the higher the melting point, and the higher the boiling point of compounds. So you're probably thinking, okay, what kind of questions am I going to need for this? Most likely, you're going to be given a table of values, okay, and asked to compare different compounds and their lattice energies, and kind of make some conclusions based on that. But for right now, that's the end of the notes. Keep in tune. We're going to kind of look at maybe how we're going to test over this and assess some of your knowledge. It was brought to my attention that some of the notes earlier on in this unit, that wasn't supposed to be there. Some of the notes earlier on in this unit haven't been completed. So what I'm going to do is, in a later video, I'm going to try to go back over and look at some of these trends that we talked about in class, and kind of make sure you feel good with periodic trends as well.